So what all this stuff is kind of leading up to is big O notation, and we'll come back to this throughout the week. And this is sort of the practical application in terms of practicing this skill, both because it sometimes comes up in technical interviews. And while it's not something you'll use in this course, you may find that you come back to this in the first couple years of your career, especially say if you are working at a company with lots of data. Like the classic real world scenario of this stuff is like an SQL query with a nested for loop hiding inside of it. But this is about our performance and how it's affected by change in input size. And that's what I've been talking about kind of with space and time complexity. Right? And we've got time and space. And I'm going to jump through a couple different resources here. There's a couple slide decks and things that I like. So I may jump around a bit. But you'll hear people talk about big O of n and big O of this and that for different data structures or algorithms. And this is what we mean. We're talking about like the worst case scenario. We're usually talking about time complexity. If someone's talking about space complexity, they'll specify it. But unless it says otherwise, you should just assume time complexity. And this notation is literally a big O, and then n with the size of our input. And then we talk about what that worst case runtime performance is. So as examples here, these are like common runtime complexities. Big O of 1 or constant time. Think about a Python dictionary. How many steps does it take up to look up my name in a dictionary of names? You know, if it's by, or actually, I guess a better example is, let's say it's by like email address to make it a little more real world. Like if you have a Python dictionary where the key is the email address and then the value is like a user profile information, you know, if you have the key, how many steps does it take to look up that user?
One.
Yeah, exactly. And that's a great example of a constant time lookup. We're not going to talk a lot about like hash maps, which is another data structure, which you can build, which is essentially similar to dictionaries with some differences, but a similar sort of idea. But a Python dictionary or a JavaScript object used in a dictionary-like fashion is a great example of a constant time lookup operation. Logarithmic time, I'll talk about in a bit, and we'll see binary search a bit later in the week. Right, big O of log n. Big O of n, linear time, we've seen already, you know, iterating through an array. And then these others, n times log n. I got that other algorithm wrong. It was like s plus n, really. But you know, you might have like two loops, and they don't quite iterate over the same thing, but they both relate to the input size. N squared, the for loop is your classic example there. And then these really bad runtimes at the bottom, 2 raised to the n, right? So not like n squared. So like for 1,000 users, it's not 1,000 squared, it's 2 raised to the 1,000th power, which would be really bad. Or n factorial, which is like 5 factorial is 5 times 4 times 3 times 2. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. And we'll look at factorial a little bit more later on. But that would also be really bad for 1,000 users, you know, 1,000 times 999 times 998. That would be massively huge. And you really only run into that. Well, for example, if we're actually like maybe implementing like a factorial or dealing with recursion, which we'll talk about a bit more tomorrow. So again, just as examples, like accessing a single element in an array. If we know where that array, if we know what we want to get, then that's a constant time operation, obviously. Binary search, we'll talk a bit on Thursday. But it's essentially a strategy of divide and conquer. Of if I've got a list of things, let's look right. Well, really, it depends on having that list be sorted. Because if my list is sorted, I can look in the middle. And if the middle's too big, I just cut it in half again and look in the middle of that first half, right? And just keep looking in the middle in whatever direction I need to. And there's sort of a bunch of different algorithms that can use that. And we'll look at a basic binary search implementation Thursday, I believe. And that ends up being log n. Big O of n, linear search, right? If we have to go through every element in the array, we have to double every element in the array. There's really no way to double every element in an array without going through, each element. If unless, we can try to be fancy with duplicates or something, but if it's unique, we have to go through all of it. The merge sort algorithm we won't look at in class. It probably will not come up on technical interviews. There's sort of like 5 or 6 sorts that are like the classic sorting algorithms that everyone learns. And I saw someone was asking a question about like what is Python's sorting algorithm, and then there were some answers there that are probably right. I actually don't know. And in the real world too, like these, like the way I learned these sort algorithms in school, it's like very sort of naive, like simple implementations. And in the real world, people add in all these things specific to the specific scenario. So like the Python sort algorithm has probably been tuned a bit. The analogy here, again, think about like a car engine. Like if you're learning the basics of what a car engine is, you kind of learn all the basic ideas. But then in the real world, when like Ford builds a car or Hyundai or Toyota builds a car, there's a ton of complexities beyond what you would learn about like learning about a car engine for the first time. And the same thing is kind of true with like how these algorithms and data structures get used in the real world. Bubble sort, you all may or may not have heard of. It's basically the nested for loop of sorts of let's start at the beginning and then go through everything else to find something like that's smaller and bring it over here and do that again. We'll probably take a look at implementing that one because it's pretty straightforward. If we get to it, I'll try to get to it on Thursday. We haven't talked a lot about this, about recursion, or like the Fibonacci sequence, but we'll see it a little bit tomorrow. But the thing to pay attention to is line 5, where you can see that this function is calling itself twice. And since it calls itself, it means it's potentially calling itself again and again and again. And so this is the kind of algorithm that can really drive runtime up. And this is an example of an algorithm that's not really worth worrying about. And we're not going to go into it, just to show an example. So you could think about trying to like randomly sort a deck of cards, or sorry, to just shuffle a deck of cards and hoping to get it in order. You have to work pretty hard, I think, to end up with something that's vectorial time. And then just here's all of these kind of on a chart, just to kind of give a visualization to get a sense of things. And you can see why programmers do start to care about this, because there are pretty huge differences in performance. And if like, again, if we're the US Census and we have to look through all US citizens, so n is a couple 100 million, there's a pretty big difference in like which sorting algorithm that we choose. This is not worth worrying about too much. You might come back to this later. Like this chart might be useful when you start to prepare for technical interviews. But basically, for different operations, such as inserting or searching or deleting, different data structures, like an array is one example, or a linked list, which we looked at. Like there are time complexities, there are like limits depending on what you're doing. Like for a linked list, like since as we kind of saw, like the only way to get to the next thing in a linked list is to iterate through the linked list. It's hard to get like a really like your worst case search for a linked list is just going through everything in it. And don't worry about this too much. Everyone will have to do a little bit of cramming on data structures and leak code problems, and grinding away at them after graduation. And that's true not just of you guys. That's like if I was working a software engineering job and I wanted to start interviewing, I would have to do some of this too, because we don't use this stuff in day-to-day software engineering for the most part. So it is sort of a specialized skill set. This part we don't really need to worry about too much, and I do want to switch us over to talk a bit about stuff, and also then to quickly look at one of the problems that we have. So we already kind of talked a bit about like the different kinds of performance efficiencies, right? Big O of 1, constant time. And here's and looking up something in a dictionary is a good example. This is a incredibly simple program that's always going to have a constant runtime, just because we're just doing this one comparison, right? It doesn't matter how big these score values get. Again, like a great big O of n linear time example. If I want to print all the elements in an array, I have to go through all the elements in an array. That's going to be big O of n, and there's not really any way around that. For big O of n squared, so here what we want to do is we want to find all the different pairs in an array and add them together. And again, it's hard to do that without like an inner loop where we're just adding things together and combining them. So the logarithm, this is really the only bit of math that we're going to touch on here. There's a couple math-like things. But the logarithm is like, so just to kind of read it out here, it's the number of times you have to divide a number by a base. And I always get confused on this myself. So what I always do is, what is log of 10 squared? That's always what I go to, because I know like 10 squared is 100. I can remember that really easily. And so this is whenever I need to remind myself what is a logarithm, I just honestly I look this up. And the answer here is 2. And in fact, let's write this in a better way. What is log of 100? 2, right? Where I'm just kind of assuming a base 10 here. Like, how many times do I have to multiply 10 by itself to get 100? Twice. And that's why I usually use like what is log of 100 or 10 squared as my like reminder of what a logarithm is. And that's why log grows so slowly also relative to something squared. And you don't have to worry about it too much, but that's really the only bit of log related stuff. And I think really the only other thing I want to touch on, and then maybe we'll quickly look at a problem, is we're not going to implement this algorithm now, but I've talked about log n. We've talked about like sort of like merge sort and binary sort and divide and conquer. And so just to sort of demonstrate, like there's a nice visualization here where we've got a list of numbers and we want to sort those numbers. And without going into like implementation details, you can see like what this algorithm does is say, hey, let's split this in half. Let's split that in half. Let's split that in half again. Now it's really easy to compare two numbers. That's not a lot of work. Let's put them in the right order. And then again, let's do that again. And then we have to compare this, but these are sorted. So comparing sorted lists is way easier than unsorted lists. Let's combine them. So this is called merge sort. And then these get combined. And you can sort of see this sort of like tree-like structure. And this is sort of what like logarithmic runtime performance algorithms look like. Because, you know, this is not like n squared. We're not taking we're not taking like 8 squared, but it's some sort of power of like n type thing. And that's why it's n times log of n here without going into too many details, just to give you a little bit of a preview. And you see that with recursion as well. And we had this here, but just to reiterate, here are some common runtime problems or runtime complexities. So your guys's assignments for today. So there's a couple LeetCode problems that are just sort of warm-ups, going back to the array stuff that we looked at earlier. And I think this should be pretty straightforward. You don't have to worry too much about big O here. It could be interesting to try and think through what the runtime complexity of these is after you implement them. But these are really to get you comfortable working with arrays and pointers and should feel pretty comfortable the problems that you've done. And I wouldn't say to spend too much time on them. Really, it is these big O problems. And then I would say if you get a chance to look at the bubble sort, which is a good one. I think the walkthrough here is pretty straightforward, and bubble sort's kind of a classic. This is just a number of algorithms, and then we're being asked to figure out the big O for each of them. And so I'm just going to grab this one, I think, and run it real quick, and we can walk through it. And actually, I should pause because I've been talking a lot and I didn't pause for questions. I do apologize. Well, I do want to check in and see if people have questions around this basic concept of big O, because I did just kind of power through a bunch of stuff there. Okay, cool. Let's do big O 2. And let me just close these out. So as always, the first thing I think I want to do is I actually want to run this. So I'm just going to make some customers. Oh, and it looks like that's a name thing, so that's fine. And what did we not like? String indices must be integers. Oh, because it wants. So that is annoying, I have to say. So let's just make this real for a moment. Forgive me here, for taking a minute with this. And we'll just keep it really simple. And unless I got my Python syntax wrong, that ought to do it. But I do see someone complaining here.
Need a comma after your first dict.
You're mute again.
Thank you. Forgive these terrible squiggles. They're mostly about indentation. What's the runtime complexity of this algorithm? What's the big O of this algorithm? Like, there's a couple ways to figure this out, right? Does anyone want to take a crack at it and just describe it, or just explain their process?
Maybe 2 times n.
Why 2 times n?
Because the loop is going through the customer list twice.
Correct. The loop does go through the customer list twice. So if I have 3 customers, how many times total do we go through it?
6.
Correct. And so you totally understood the complexity correctly, but that is actually n plus n, right? And this is actually the same mistake that I made that Shannon pointed out before. N times n would be some, not necessarily a nested for loop, but somehow, you know, like related to this. Like, and in fact, if we make customers bigger, like if customers was 10, then it becomes a little clearer. Right, which one of these looks more like the actual number of operations that this program does for a list for 10 customers? Are we going through 10 times or 100 times? Or 20 times or 100 times, excuse me.
20 times.
Yeah, exactly. So you had the right idea. You just made the same mistake I did, which I just sort of jumped to conclusions. So this algorithm is big O of n plus n, or we could really say big O of 2n. I'll just say n plus n. Really, we could simplify this to big O of n. For the exercises today, it might not be worth it. But the reason being, again, is like, you know, if n is 1,000,000, I don't care about 1 versus 2,000,000. I care about 1,000,000 versus 1,000,000 squared. But I think for today, it's better to do it this way. If, you know, I'm not sure. Yeah, it'd probably end up being like quadratic. Like if we had a nested loop at that point, it's like exponential. And so the way to do this, I think, is exactly kind of like we did. Like, take a look at it. You know, sometimes it's helpful to walk through it and you can just come up with a number with a big O value, but it's really useful to come up with a couple real world, like actual data, and then walk through that to double check your assumption and honestly double check your math. Because it's just like I kind of made that same mistake earlier. It's an easy mistake to make. And do folks have questions about this particular algorithm, as long as we're looking at it? Cool. So that one hopefully feels pretty comfortable and straightforward, and that's the goal. They start to get a little more complex. Like right around here is where it starts to get interesting. we haven't really talked a lot about the insertion sort algorithm. But that's what's going on here. And we've got a while loop inside a for loop, and there's a key and there's J. So this is where I think it might start to get a little more complex, and where you're going to be wanting to write out like, all right, well, I know this outer for loop is going, this is going to be n, and then it's got to be n times something, because I've got another loop inside of it, right? So I have to figure out how many times does this while loop go through, and multiply it by n, basically, with the for loop is probably what's happening here. So this is where it starts to get a little more complex. And I would definitely say, if you want to like work in groups on this, that there's value to it. You know, some of these are a little more straightforward. Like this one is obviously more straightforward. And then implementing bubble sort, I think, will be fun. That will be a good one. There is, if you get through all of this stuff, there is sort of another lecture material that we have that talks over big N again, and actually gets into a little more complexity. But starting with the assignments is really a good spot. And in fact, one of the nice things about these big O problems is we have some reading here that we really recommend doing that is quite good. Just I would maybe start on like a couple problems, and then, I mean, the how to calculate article, both of these are relatively short. Actually, I would recommend just reading them through. And I think just the one last thing I want to show quickly before we wrap, because I know we're at time, is let's see, where are we hiding? Forgive me. There we are. In the other PowerPoint slide deck. All this stuff we pretty much covered in the other ones, but there is a great YouTube video here, and I'll throw this in the Slack channel. I know we haven't talked a lot about these search algorithms, but if you look at the bottom left, which is bubble sort, which is big O of n squared, which is essentially like the nested for loop approach. And the merge sort one over here, that was the sort of divide and conquer approach. That was n times log n, that there was that sort of tree-like structure for. And what these little flashing things represent is like the pointer. You know, if you've got a for loop, it's the pointer moving through. And it can't, don't worry about this too much, especially if this is sort of feels like I'm looking at Greek right now. But it can be really interesting just to sort of visualize some of these things and like the time complexities. And it makes a pretty big difference. Like, if nothing else, like let's look at merge sort and bubble sort again here. So bubble sort here, think nested for loop, think big O n squared. Merge sort, think n times log n. Think merge sort is in fact I really want to find that diagram just to show it again. This is merge sort. Think dividing and conquering, dividing, and then merging. So that's, I think, the one thing to look at here. Here we've got n times log n, dividing and merging. Here we've got the big O n squared nested for loop approach with bubble sort. And just look at those two and look at the difference in what they're doing and their efficiency and how quickly merge sort gets done. So that's a great visualization of the real world impact of these algorithm efficiencies. Computers are so fast these days that it's very hard for us to really see that. And because we're using like these really powerful tools like the Python language where everything has kind of been tuned for us, like we don't have to think about it. But I think it is useful to see this visualization. And I'll throw this in the chat. So that's it. I ran a bit long. Thank you everyone for sticking around. And yeah, that's it. I think we have some good assignments, and I hope everyone has a great lunch. And